In this video, we're going to do another example where you have to predict if a precipitate will form when mixing two solutions together. So as usual, you do need to write a double displacement reaction and predict which substance is your precipitate and which substance is not your precipitate. In other words, still dissolved. So you have part of the double displacement done for you here. It's important to make sure it's balanced. So I've had to put a 2 over here. And then the lead looks balanced. Everything else looks good here. These are your solutions that you start off with. So they're just going to be aqueous. And then afterwards, we have to take a look at our solubility table to predict which one of these is soluble and which one is solid. Generally, the nitrates, as we know, they are going to be soluble. So I'm just going to put that as aqueous. But then for my lead sulfate, I'm going to go take a look to see if that one is soluble or a precipitate. So lead sulfate. So sulfate is the ion. And it says that essentially, right here you can see lead with sulfate is insoluble. So right away that tells us that's our precipitate. And then we have to figure out if this will actually precipitate. We have to do our QSP versus KSP comparison. So that's our step 1, writing out our balanced equations. Step 2, let's write out a dissociation equation for the potential precipitate. So PbSO4 solid is going to form some Pb2 plus AQ plus some SO4 2 minus AQ. And so we need our QSP expression. QSP is going to be equal to the concentration of the Pb2 plus times the concentration of the SO4 2 minus. And then we can also get our KSP from the table. So lead sulfate, its KSP is going to be, so lead 2 sulfate, 1.8 times 10 to the power of negative 8. So it's not very soluble. 1.8 times 10 to the power of negative 8. Let's go take a look to see if that was actually correct. Right, okay, good. So that's correct. So now we need to find the concentration of each of these ions by looking at the compounds that contribute those ions to the solution. And we have to make ice tables for each of those compounds. So we're going to start off by taking a look at the lead concentration. I'm going to keep some room between step 2 and 3 so I can just finish up the problem back on step 2. So for step 3, I'm going to do, so lead comes from lead nitrate. We'll make our equilibrium expression or equilibrium dissociation equation. Plus 2 nitrates. We don't really care about nitrates because they're not in our precipitate, but we're still going to write it out to make sure our equation is balanced in the end. The concentration of the lead nitrate in the initial solution was 1.6 times 10 to the negative 4. We know we had 0 of the ions before dissolving. After dissolving, we're going to have plus x plus 2x. We don't really care about the 2x because, again, it's a nitrate and it's not in our precipitate. This would be minus x over here, and this would be 0 because all of it was dissolved. So what this means is that, therefore, x, which is the concentration of the lead ion in that volume, is going to be 1.6 times 10 to the power of negative 4 molar. Keep in mind this is in the initial volume. We had 255 milliliters in the initial volume, and then the other substance, the other solution was 456 milliliters. So together the new volume, V2, the two volumes added together, is our 255 plus our 456. We get 711 milliliters, or 0.711 liters. So we need to use our C1 V1 is equal to C2 V2 to find our C2, which is C1 V1 over V2. And so it's going to be 1.6 times 10 to the power of negative 4 molar times the initial volume for the lead nitrate was 255 mils, or 0.255 liters, over the new volume, 0.711 liters. Cancel out liters, and we get our new concentration. So we get 1.6 times 10 to the power of -4 times 0.255 divided by 0.711, and we get 5.7383 times 10 to the power of negative 5. So that's our concentration of the lead. And so we can write that in there as 5.7383 times 10 to the power of -5. And now we're going to have to go do the same thing, but to find the concentration of the sulfate. And that comes from the sodium sulfate. Now, one thing to mention, which I forgot to mention earlier, I didn't really have to go look at my solubility table to find which one was going to be my precipitate. Notice in the question, it tells us here, it says, would a precipitate of lead 2 sulfate form if this and that is mixed together? And then they also gave us the KSP value, so I didn't have to go look. But I want to show you where you'd find the information if it wasn't provided to you. So now we'll make our ice table for the sodium sulfate. We have 2 sodiums. We don't really care about the sodiums because it's not in our precipitate. What we do care about is the sulfate, since the sulfate is in our lead sulfate. So we'll have our ice. This was 0 to begin with. This is plus 2x plus x. This is 2x and x. We don't really care about the sodium again because it's not in our precipitate. We know this will be minus x and this will be 0 because all of the sodium sulfate was dissolved in that solution. And the initial concentration is 2.3 times 10 to the power of -4. So 2.3 times 10 to the power of -4. And so what that means is that x, which is the concentration of the SO4, is equal to 2.3 times 10 to the power of -4 molar. But don't forget this is in the initial volume, so we have to find this in the new volume. So C2 is equal to C1 V1 over V2, which is equal to 2.3 times 10 to the power of -4 molar times the V1, which was 0.456, 456 mils for the sodium sulfate. So 0.456 over the new volume, 0.711 liters, cancel out liters, and we get our new concentration. So we get 2.3 times 10 to the power of -4 times 0.456 divided by 0.711, and we get 1.4751 times 10 to the power of -4 molar. So we can go ahead and plug that in here. 1.4751 times 10 to the power of -4. And we can plug all this into our calculator to get the KSP value. So 5.7383 times 10 to the power of -5 times our other concentration there gives us I have to retry that because I inputted this wrong. Let me retry this again with the right mode for my calculator. 10 to the -5 times 1.4751 times 10 to the -4. Let's retry that again. Okay, let's press equals. Whoops. And let's try it one more time. Now it should work. Another calculator error, 5.7383 times 10 to the negative 5 times 1.4751 times 10 to the negative 4. And we get 8.4645, so on and so forth, times 10 to the power of negative 9. That's our QSP. So as you can see here, if we want the QSP, it would be to 2 sig figs. So it would be this value over here. So you just have to make sure that it is to 2 sig figs. But this QSP, 10 to the negative 9, is smaller than the KSP. So what that means is that the solution is unsaturated and no precipitate forms. No PPT precipitate forms. And so this is just another example of predicting a precipitate will form using the KSP and QSP comparison method and a variety of ice tables from the compounds that form the precipitate. There is another example that you can try over here, and you can take a look at your answers over here, or at the long answer within the filled in version. This one's a bit more straightforward because you have a balanced equation for you. And you're also told your precipitate as well.